Hey everyone, today we're solving a problem. We're given a collection of intervals. We're finding the minimum list to remove so that the intervals are not overlapping at any point. I'm going to cover the brute force approach, then optimize it using the greedy method, explain how we do that and the techniques that we use, and then I'm going to demonstrate it with a diagram. So I already have the brute force method laid out here. At the top is a sample input, and right below is the sorted input. And it's sorted based on the second index of each of the lists. In either approach, we need to sort the input first, as the solution or the interval that we always want to start with is the interval that has the lowest end point, so it's second index. And the reason for that is because if we start with some of the higher indexes, then it could cut out too many of them, or it could cut out some of the most optimal, where we know that anything that overlaps with the first definitely needs to go. Using the brute force, we take in our array and then we sort it. So this is of n log n complexity, but in the end it ends up being shadowed by the inefficiency of the solution. In a nested for loop, we're using our helper function to determine if the second pair's start, so its 0th index, or its first index, would be in between the end or the beginning of our first pair. So if we consider pair 1 is 1 and 2, and pair 2 is 3 and 5, we check if 3 is in between 1 and 2. If we have determined that it is, then we would add it to the list that we've already seen it intersects, because with some we'll see that it will intersect, maybe it intersected with the first and it would also intersect with the fourth, but we would only need to remove it from that list one time. So we check each time if we've already removed this theoretically. And then finally, we'll just return how many we needed to remove for there to be no overlaps. And like I said, this is quite an inefficient solution. So even though our sort would be n log n, due to these loops right here, we end up with a complexity of n squared plus n log n, and the n squared will shadow or overwhelm the n log n, leaving us with an overall brute force time complexity of O(n) squared. So now we're going to solve this using the greedy method, and it's actually a fairly simple solution. Again, we need to make sure that we take in our input and we sort it. And again, this will be n log n. And we would have to pass it a key as well to specify that we're sorting based off of the second index, but that's all right here. And then we would set our first element that we would compare all of the subsequent elements against to be our first. So we're comparing the end element against all the future ones to determine that the end is not overlapping with the next start. So in this case, it would be 2, but here we're going to take n 0, 1. So the first element's second index. And then from this point on, we iterate over all of the remaining, and we check, and we would check from 1 past the first. If the pair is greater than or equal to our previous closed, then we can extend our interval here, or we know that it's acceptable and not overlapping. So our new closed would be equal to this pair 1. Otherwise, we'll have removed one more element. And that's really all there is to the greedy method. And this is O log of n, or O in log of n plus O of n, and that is the O of n is shadowed by the O in log n. So our overall time complexity is O of n log n. Now we're able to do a greedy method here because the locally optimal solution leads to the globally optimal solution, and this is because of how it's sorted. Knowing that our first sorted element cannot overlap with anything to the left, and it gives us the most space for more on the right, leads us to this being the first optimal solution. And then from there, just comparing with the previous closed, we can determine if we can add it on without eliminating any of the further solutions on. So this is the optimal substructure of it, and it's only when it's sorted. And that is what allows it to be done with the greedy method. Finally, to demonstrate this pictorially, we have our input array and our sorted array. Based on this, if we were looking at it as a number line, this is the range of our start to our max end. With our start, we know that this is optimal and that nothing else will conflict with it. Based on that, we would check if the next start is greater than or equal to our last start, which it is, and we'll currently have 2 stored. So we know we can do this as well. And you can see that there's no intersection. It's fine for there to be a gap, but something that was previous to this would not be okay. Now we'll have stored 5, as that's our previous closed, and we'll check if 5 is greater than or equal to 5, and it is, so we can add it. And something that looks like that is okay, as there's no doubling back over itself. Then we check if 4 is greater than 6, which is not. That would look something like this, and we can't do anything like that, so we have our first one that we need to remove. So our removed is +1, and our closed would be 6. And then we check if 5 is less than or is greater than or equal to 6, which again, it's not. So we can't do this either. So our removed goes up once more, which leads us to 2 as a solution.